Anything here before we jump into things? Okay. Any more questions on anybody or no? That's okay if you don't. We can always, I'll ask again next time. You're like, I just haven't been far enough in to have anything to ask about. Like I get. It's part of the long deadlines, is I know you're not going to be all the way through everything all the time. Or that you have opportunities to like go back and like Google some stuff and look things up and, you know, it's fine. Okay. So if anybody finds anything, let me know, but I'm going to talk a little bit about test format here for a bit. So the test is in 2 parts. So the first part is going to be like 5 problems. For the most part, that'll be like take the derivative of this thing. And then 2 FRQ questions. So I'm going to say FRQ questions. It's like saying ATM machine. The Q is question. Like 2 free response questions. Anyway, and part 2 is the calculator section. So you have 10 multiple choices there and then 1 free response question. So skills that you should be able to demonstrate: taking the derivative of the function involving combination of the derivative rules, including but not limited to quotient, chain, power, trig, exponential, logarithmic, inverse trig, etc. So basically we have all the derivative rules. You should see problems that throw them at you in combination. There would not be anything so bad as like the back page of that derivatives practice where I had like a million things going on at once. But you could see something like with an inverse chain and a chain and inverse trig rule. Or you might see a product inside of a quotient. Or you might see, you know, like you should be able to see like some combination of these things. It won't be like a satanic combination, so. Okay, maybe a double chain, or a problem where like it looks real bad at first glance, but you can algebra your way down to making it really manageable. You know, if you have the natural log of some nasty looking thing, but you can like break it into a bunch of individual chain rule problems. Anyways, you should be able to use your calculator, take the derivative of a function at a point. We talked about doing that, right? In class, we ran through how to use the calculator to do that. Correct or no? Yeah, okay. You should be able to calculate the derivative of an inverse at a point. We spent a day talking about that. That was like the bonus inverses thing. You know, where the derivative of g prime is 1 over f prime of g of x. Should be able to find the first derivative using implicit differentiation, or the second derivative using implicit differentiation. You should be able to write the equation for a tangent line to a point. If I give you an implicitly defined curve, like you did on the homework quiz, right? You should be able to find the linearization for a function and use that linearization to approximate values of f of x. And give an error for the approximation. Hi,
Mr. Druid, can I have my test?
You didn't have it?
I don't.
Well, I'm so dumb. Yes, so it should go under Chapter 13, correct?
Yep. Oh no, not that one. Chapter 14.
Oh, 14. Is it it's the quiz?
Yeah.
Then. Oh, that's why I didn't do it. Yes, I completely didn't put that together. Yes, I give you one. Are you in fourth period?
Yeah. I'm in study hall. I'm in fourth hour.
Okay. My apologies, Kevin. I was confused at what we were doing. You too. Questions about topics? All these things sound relatively familiar, I hope. Pete?
Is there like a set what you want us to stop simplifying for these ones too?
So any problem that I want you to test you on the simplification, I would put as a multiple choice question.
Okay.
So anything that's free response, you can stop when the calculus is done, just as it always has been our standard, will continue to be our standard. So if it's a free response question,
So
I don't need you to simplify things to make it pretty at the end.
okay.
If I want you to test that you're able to simplify and get it to look pretty at the end, I'll put it as a multiple choice question where like you're forced to, simplify enough to where you get the answer. Does that make sense? Okay. Yes, Adrian.
The d squared y over dx squared, that's just second.
Correct. Yes, that's the notation for a second derivative. Correct. 100%. You could write y double prime if you prefer using the prime notations.
Did you record the using your calculator to take the derivative of a longer or derivative of a function at a point?
Did I record that part?
Yeah,
I think so.
Okay.
It would have been on Halloween, right?
Okay.
I think is when we would have done that. Because we redid this on the calculator, right? I think we did that on Halloween.
Okay.
If it's not there, there's a problem, let me know and we can go through that again next time. I'm happy to do that again. Okay. Sound okay with you guys? So I put together some sample multiple choice questions and free response questions from the MyAP to help review some of those skills. We've done a lot of practice on like taking derivatives of things by hand. I feel like you'll probably feel like you're in a decent spot on that sort of thing, right? Or no? So usually the multiple choice stuff and the free response stuff is the place that's kind of the scariest or the most unknown as to what to expect. So I would definitely spend some time in here kind of working through things. Again, the keys are up. But let's kind of buzz through and do 20 minutes of this stuff and then we'll change gears. Sound good? Okay. So I'm gonna start maybe with some of the FRQ stuff at the end. So this is an example. This one says a graphing calculator is required for the question. So this is an example of something that would land on the calculator portion of your test. So it says, there's a bunch of preamble or whatever, but you're given this little table and it says the depth of snow in a field is given by the twice differentiable function s for 0 less than or equal to t less than or equal to 14, where s of t is measured in centimeters and t is measured in hours. values of s prime of t, the derivative of s, at selected times t are shown in the table above. It is known that the graph of s is concave down for 0 less than or equal to t less than or equal to 14. Use the data in the table to approximate s double prime 10. Show the computations that lead to your answer. Using correct units, explain the meaning of the second derivative of s at 10 in the context of the problem. Okay, so there's like 3 things that we need to do for part A, right? We need to make the approximation, we need to give it the correct unit, and then we need the explain in context what this is. So how would we do the approximate the second derivative of s at 10? Good. So the key there is approximate, right? Whenever you're asked to approximate a derivative, the method you would be using is slope. So 10 lies in between these two. So this would be approximately. Everybody's okay with that? And it's a calculator problem, so you just grind that through on your calculator. What should the unit be on this? So what's the unit for the numerator? Centimeters per hour, right?
Centimeters per hour squared.
And the denominator is hours, so our answer should be centimeters per hour or per hour squared. That's correct. Is everybody okay with that idea? So again, if you just look at the unit, when you do the slope calculation, that'll tell you the unit for the derivative that you just approximated. Is everybody okay with how I did that? Again, fairly easy if you know what to do, right? If you've practiced doing that. And then the last part of the question says, explain the meaning of that second derivative of s at 10 in the context of the problem. What's that? So it's not a motion problem though, right? What is the context of this problem? We're talking about the snow, like something that's snowing, right? The depth of a snowfield. So you should say at time t equals 10 hours, now, a second derivative is a rate of a rate, correct? So you would say so at time t equals 10 hours, the rate of change in snow depth is whatever centimeters per hour squared. Are we okay with how we worded that? So again, if you're a second derivative, you're a rate of a rate. Part B says, is there a time t from 0 less than or equal to t less than or equal to 14 at which the depth of the snow is changing at a rate of 2 centimeters per hour? Justify your answer. When you read this, what does this sound like? Excellent. Yes. This should sound like an intermediate value theorem question. Okay. What's the first thing we need to do for an intermediate value theorem problem? Not constant, the other C word. Continuous. Why do we have continuity? Because what? Yeah. So we can say since S prime of t is twice differentiable, S prime of t is continuous, and since S prime of 8 equals 9.8 is less than or equal to 2, less than 2.1, which is equal to S prime of 3, the intermediate value theorem states there exists a C on the interval from 3 to 8 such that S prime of 3 is equal to 2. Everybody okay with the language and the verbiage? That all should sound familiar. That's the same way we've done this before, right? Notice that these first two problems are just like rehashes of things we've already done, right? There's nothing new conceptually that's happened, even in like test 3 topics yet. This is all, these first two parts were just stuff we'd already done. C says at time t equals 8, the depth of snow is 45 centimeters. Use the tangent line to the graph of S at t equals 8 to approximate the depth of snow at t equals 10. Is the approximation an underestimate or overestimate of the actual depth of snow at time t equals 10? Justify your answer. So here is something that's going to be new, at least like a test 3 topic. It's not something that's prior learning. What are we really doing in part C here? It's asking us to do a linear approximation, right? That was the last topic we had talked about just ever so briefly last time. So I'm going to start by writing my equation for my tangent line. So this first piece of information is like my point. And this value of the derivative at 8 is going to be my slope. Is everybody okay with that? So I can say that S of t minus 45 is approximately 1.9 times t minus 8. So far, so good. So if I want s of 10, I just plug 10 in and there's my value. Vinny? There's the decimal one, just really small. I put it there, just I was going fast, it's just a dot. But yes, it is 1.9, 100%. So far, so good. How are we going to determine if this is an overestimate or underestimate? Because we don't know anything about the actual value of S of t. So looking at a graph is going to be the idea. You're right, Adrian. But we don't know anything about what the graph of S of 10 is going to look like. But we are given this, that the graph of S is concave down. So that's my graph of S. If this is my point here, say this is like t equals 10, or I'm sorry, 8. We draw our tangent line, it's going to look like that, right? So this point here would be like 10, comma, our linear approximation at 10. And this point would be 10, comma, like S of 10. So is our linear approximation an overestimate or underestimate? It's an overestimate, right? Because it's higher than S of 10 should be. Does everybody feel good about how I was able to work that out? Now that was tricky, right? On how to come up with the reasoning there. But hopefully you're like, read this and like, what the heck am I going to do with the concave down? How does that matter at all to me? This is where it mattered. This is how you're using that. Does that feel okay? And again, the picture I think is a worthwhile justification, right? Add a little bit of words to that, but yes.
So how does it being concave down affect that it's overestimate? Like, wouldn't it do the same thing as concave?
Well, if it was concave up and we did it, right, it'd be an underestimate now. Does that make sense?
Yeah.
So it absolutely matters. And the fact that it's only one thing over that interval makes a huge difference. If it could be both, then we can't say without more information. You know, it depends on where that change in concavity happens. So far, so good? And then for D, it says the depth of snow in centimeters is also modeled by the twice differentiable function D for 0 less than or equal to t less than or equal to 14, where d of t is equal to 120 minus 92 e to the negative t over 40. And time is measured in hours. Use the model to find d prime of 10 using correct units. Explain the meaning of d prime of 10 in the context of this problem. So again, kind of three things to do there, right? We have to find the value for d prime of 10. We have to give the correct unit and then explain what that means in the context of the problem. Okay. How are we going to find d prime of 10? What's going to be the best way to do that? Okay. What do we need to do that though? can do it that way, but what should you really do? Type it into your calculator and have the calculator find the number for you, right? If it is calculator active, and you can do it just typing it into your calculator, I would write that for my work, and then I would type it in my calculator and press enter. Okay, so inside y equals 120 minus 92 second e to the negative x divided by 40. You could also do this into the main screen, but if you have to do anything else with it, with that function, which I guess we don't in this problem, I always just type it to y1. And then we'll do math and derive x. We'll do y1 here, so vars, y vars, function y1, and then 10. So there's my answer, about 1.79. That's like the first piece of this. It then asks for the unit. What should the unit for d prime of 10 be? Remember that d is the depth of snow in centimeters. And t is measured in hours. Centimeters per hour is correct. And I guess this should be good too here, technically. Is everybody okay with how Adrian came up with that? Again, the first derivative is a slope. The y unit is centimeters, the x unit is hours. The slope will be centimeters per hour. Everybody's okay with that? And then the context, what this means in the context of the problem, we'd say at time t equal 10 hours, the rate at which the depth of snow is changing is 1.79 centimeters per hour. Or something like that. Right, we've related everything back, everything has a unit attached to it. It's in the context of the problem. You use the word rate. I suspect those are the things that your AP grader would be looking for in this kind of a problem. That feel okay? And now this part D was decidedly a test 3 topic as well, right? Where you would have had to use the chain rule if you tried to do it by hand. So far so good? Okay. I'm gonna stop here. We've been in this now a half hour. We'll kind of continue to take some time and circle back to these problems. We'll do it again on Thursday or Friday, and we'll do it again on Monday or Tuesday, and just kind of keep circling back in here. As you've gotten a chance to go through and look at these things, like make notes of things that you're like, I want to talk about this one, or see what Mr. Kulik says as to what to do it, especially the multiple choice where the key is just the letter. But try to get to the free responses at the end. I mean, there's 3 free response style questions on the test. So I would make sure to spend a little bit of time preparing on those. Everybody feel all right, though, all things considered? What we're going to talk about for the rest of today, and we'll talk about this again a little bit on Thursday or Friday, and then Monday or Tuesday. We're going to just kind of stretch this section 3.9 out over those 3 days as well, as long as we're going to do the review. My experience tells me 3.9 is the most difficult topic we do in first semester for students. And it's not because the mathematics is particularly difficult, it's because it's story problems.
It's 3.9 on the test.
3.9 is on test 4, not on test 3. So it is on a test, just not the next test. Fair enough? Okay. And again, the problem is not that the calculus is so difficult, because there's no new concept happening here. If you can do implicit differentiation, you can do this. It's no harder than implicit differentiation is from a calculus standpoint. The problem is you're not given the equation to start. You're given a story that you have to translate into what you need. So, hi Ashton.
One test.
Sure, come on in. Yeah. Right, so you're gonna be opening these 5 accounts, right? There's 5 ledgers for you to open. And then this is your journal.
Oh,
So you're gonna be translating those amounts into your ledger. Yep, does that make sense?
Yeah.
Okay. So I copied from the textbook their strategy for dealing with these sorts of related rates problems. That's the topic that we're talking about, are related rates, by the way. So read the problem carefully, draw a diagram if possible, introduce notation, assign symbols to all quantities that are functions of time. And really that's the part that, like, naming things appropriately can be so helpful. Like if I name everything for you, you can probably do it a lot easier than if you're unable to name the things, or having to name the things yourself. Express given information and the required rate in terms of derivatives. That's part of naming, in my opinion. Write an equation that relates the various quantities of the problem. If necessary, use the geometry of the situation to eliminate one of the variables by substitution. We'll talk about examples like that, maybe not today, where we have to eliminate a variable. That's the most difficult version of this sort of problem. Use the chain rule to differentiate both sides of the equation with respect to time. That's basically doing an implicit differentiation. And then substitute the given information into the resulting equation and solve for the unknown rate. So, let's kind of go through some examples. Today is going to be mostly like me doing examples. You guys will ask questions about it. I want to just kind of build some intuition about like how this process works, why I'm doing the things I'm doing. And then in the subsequent classes, I'll do a few examples, but mostly you're going to practice in like an in-class setting where you can talk to your classmates and make mistakes and ask questions and practice, build some intuition for yourself rather than just watching. Okay? So it says air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So everybody everybody understand what's happening? You're basically blowing up a balloon, right? And the balloon is changing, its volume is increasing, it's inflating. As its volume increases, necessarily the radius is going to be increasing at the same time, right? Everybody feel good about the picture you're envisioning in your head? Okay. There's no triangles to draw here, so there's not much of a picture to draw, but so there we go. There's our picture. There's a sphere. So let's introduce some notation. We have really two variables happening here, right? Volume and radius. Everybody agree with that? Why am I not worrying about diameter? Because it's just 2 times the radius, right? So I don't really care. I'll rewrite diameter in terms of a radius later if I need to. Are both of those variables, or are they constant? As air is being added in, is volume changing? Is radius changing? So they're both variables with respect to time then, right? Depending on how long we've been pumping air in, those things are both going to be changing. Okay, so these guys are variables. And I'll write with respect to time. Okay. Let's express what we're given as derivatives. Okay? Volume increases at a rate of 100 cubic centimeters per second. That is a rate, correct? A rate should be written as a variable. So the variable or as a derivative. So this derivative would be dV, because volume is changing. And what else is changing with it? Time. So this would be dV dt. And then it says increases. So I know my value is positive. 100 cubic centimeters. Everybody okay with how I've written that 100? Okay. The next says is how fast is the radius of the balloon increasing? When the diameter is 50 centimeters. What are we being asked for to find? How fast is the radius increasing? That is also asking for a rate, correct? How should we rewrite that rate? It should be the derivative dr dt. Everybody okay with that? But it's not asking for just any old dr dt, because that maybe is not a constant. It's asking for it at one specific moment, right? What moment is it asking for? When the diameter is 50. So I'm going to say when d is equal to 50. Is everybody okay with the notation that I've introduced here? Adrian.
Why is it over centimeters for the dV dt? Why is it like centimeters cubed over?
Oh, because I screwed up and should put second. Thank you. Yes, that's just a mistake. Very good. Thank you. Something looks wrong and you're like, I'm pretty sure that seems wrong. Like, if it's not wrong, I really want to know why, but it might just be wrong. Please ask. Yes. Very good. Lucas.
Well, isn't R in the X? So why would we need R here, not radius?
Okay. So we will eventually turn that into a radius, yes. So good point. But I didn't want to do that until I've written the equation to justify why we don't need a diameter there. Okay. But yes, you're 100% on. My two variables are V and R, correct? What equation relates volume and radius for a sphere? It's the geometry formula for the volume of a sphere. Again, if you don't remember that, that's okay. But if I write it, it should look familiar, right? I wouldn't expect you to memorize some of these more complicated volume formulas. Area ones, basic area formulas, yes, I do expect you to remember, like a triangle is 1/2 base times height, or a circle is pi r squared, or something like that. The volume ones I'll probably give you. The textbook probably wouldn't, but like just look them up if you need the volume formula for a cone or a pyramid or something. Like, it's fine.
Like the AP.
They would probably give you a volume formula if you needed it. Just in the context of the problem. Okay, so that's our equation, right? Now notice that D doesn't appear anywhere in this equation. So as Lucas has suggested, let's rewrite the diameter as a radius instead, because we know that this is the same thing as R equals 25. Everybody's good? Okay. So now I have an equation. I know stuff about dv dt, and I want to know stuff about dr dt. My equation doesn't have any derivatives in it, right? What I'm going to do now is I'm going to differentiate both sides of the equation with respect to time. So I'm going to basically be doing like an implicit differentiation on this equation. Is everybody okay with what I've written there? What's the derivative of v with respect to t? Okay, 1 dv dt. What's the derivative with respect to time of 4/3 pi r cubed? Okay, 4/3 pi 3r squared dr dt. Everybody agree with what I've written? And notice we can do a little bit of cleanup here. Pew pew. Right, that's nice. I think when you mentioned, when I asked, you already did that intuitively. I wrote it out so that everybody else would catch on, because it wasn't super obvious what had happened there. But I heard you give me the simplified answer, which is fantastic. Okay. So what we're looking now for, remember, is dr dt when r is 25. We're told dv dt is constant, so that's going to be 100 no matter what. feel good? So just divide both sides by 4 pi times 25 squared. And what does that simplify down to? 1 over 25 pi, I think. And again, if you gave a decimal there, that would be fine, right? Your teacher's a maniac and will keep everything exact as long as he can, because he's convinced every single one of these questions is a no calculator question. How did that feel, what we did there? And I guess we should have a unit on that, right? Centimeters per second or something. Now, when it came down to actually doing the problem, you had the equation and you had the variables named intelligently. To do the derivative and plug stuff in and solve was not difficult, right? That was the easiest part of the problem. The hardest part is understanding what's going on, naming things in ways that make sense, figuring out the equation that you need. That's the hardest part. The calculus piece is usually pretty easy. The algebra piece is usually pretty easy. It's the start that's the hard part. You guys get what I'm saying? Okay. Let's continue just kind of grinding through some more examples. Again, I'm going to walk through these things painfully slowly in the beginning, because I think it's important that we build intuition to have the ability to do these later. So pretty good. Was this first one okay though? That felt manageable? Or no? It's like the easiest version of the problem. So if it's a problem, like you need to say something now and we can talk some more and clear up anything that needs to be cleared up, because it doesn't get easier than like that kind of version of that problem. All right. Next one says, a ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? And you read this and you're like, woof, Mr. Kulik, this all of a sudden felt like a big jump up in difficulty for a situation. Did you guys read the problem and understand kind of what's happening physically? Right? You have a ladder and it's kind of doing, like sliding away from the wall and falling down. Like anybody that tried to lean the ladder up against the wall has probably made the mistake and had it slide out on them at some point, right? Everybody's okay? So I'm going to start by drawing a picture. Everybody cool with my picture of the ladder? Okay. Let's start now by naming the relevant parts of this picture. So it seems to me that we're going to need like this piece, and this piece of the ladder, because the shape that I've made is a triangle. Probably the side lengths of the triangle are going to be the things that I care about, considering there's nothing about an angle anywhere in this problem. Would you agree? So I'm going to name this bottom piece X, this piece y, and this piece z. You guys all right with the names? Of those quantities, x, y, and z, which ones are changing with time? X and y. Z, though, is constant, right? Why is z constant? Because the ladder didn't get any longer or shorter when it's falling. It's the same length the whole time, right? So x and y are both variables with respect to time. WRT just means with respect to. And then z is a constant. And now let's kind of start introducing some variables for the quantities that are given, right? It says if the bottom of the ladder slides away from the wall at a rate of 1 foot per second. Okay, what kind of quantity is that? It is a rate. So as a rate, how are we going to, what kind of variable are we going to give it? It is a derivative, right? What derivative name should we give the rate for the ladder sliding away from the bottom of the wall at 1 foot per second? dx dt. Very good. Everybody agree? Because x is representing the length, how far the ladder is from the bottom of the wall, right? Is dx dt increasing or decreasing? Increasing with time, right? Because the ladder is sliding away from the base of the wall. So I know that's positive. It then says, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So it asks, how fast is the top of the ladder sliding down? What type of variable or what type of quantity is that? It's also a rate, right? It's asking how fast. Speed is a rate. How should we? So because it's a rate, its variable type is a derivative. We should name that derivative dy dt. Everybody's okay with why I did that? Now, we want that dy dt, though, at a specific moment. It's asking it when the bottom of the ladder is 6 feet from the wall. How do I add that? Good. X equals 6. That's correct. And I want to point out one other observation I would make at this stage. What else can we say about the value of dy dt? It's negative. Excellent. How'd you get that, Anthony? Sliding down, right? So the other way you could think about it is as time changes, that length of y should be decreasing. It should be getting smaller. Its derivative should be negative. I'm going to make a note for that on my paper. so that if I make a mistake and I don't get a negative answer, I'm going to know that, like, oops-a-daisy, I did something wrong. That needs to be negative. I can tell from already that's a little self-check along the way, right? Everybody feel good? Okay. So now I've named everything, right? I have a picture, it's labeled. I've named the variables and the quantities given to me in the problem. What I need to do next is to write an equation that relates x, y, and z together. What equation would I write here? The Pythagorean theorem seems like the obvious one, right? If you have three sides of a right triangle, that would be what I would use. Considering we're given nothing about areas or volumes. And if I want to even here, z is constant. It's not a variable with respect to time. So I can just put the 10 in right now, right? That's not changing regardless with time, so it can be a variable. I cannot plug 6 in for x, because that length of x is changing all the time. That's not a constant. That x is a variable. It's just asking what happens when the variable of x has the length, has the value 6. Everybody see the difference between z and x in that regard? Really important. Like, these are stuff that's like, when I'm saying it and I'm doing it, it seems so obvious. But when you do it on your own, it's like you really have to sit and think about it, right? So I really want to, like, talk through what's happening in my mind while I'm thinking about this kind of a problem, so that you can see how to think about it the best way. Everybody still feels okay? Okay, what do we do next? We differentiate with respect to time. So we basically just we're doing an implicit differentiation, right? So what are we going to get? Excellent. Perfect. Absolutely. Thank you, Anthony. Everybody happy with how we differentiated? Okay. Let's plug some stuff in. So we are, again, looking for dy dx when x is equal to 6. So I can plug in 1 for dy or dx dt and 6 for x. Uh-oh, though. What do we don't have a y. How do we find the y? What do we do wrong? We're missing the variable. What's that? No, y is a length. dy dt is a rate. But y is the length, right?
Okay, so it's use of the other two.
Yes. So when x is equal to 6, z is still 10. Right? So y should be 8. Is everybody all right? So notice that y isn't always 8, but at the instant that I care about, when x is equal to 6, y has to be equal to 8 because the Pythagorean theorem still has to hold because it's still a right triangle. Is everybody okay? And now I can just subtract 12 from both sides and divide by 16. And I'm getting a negative value, which I love. Because I knew that was supposed to happen. What do you guys think on this one? Quite a bit more complicated than the previous one, at least from like understanding the setup and naming things. There's a lot more names going on. There's some things that were constants and some things that were variables. Some quantities that were rates and some that were not. But hopefully that felt understandable as we kind of worked our way through it. Does it feel okay so far while I'm doing it with you guys? Because when if it doesn't feel good now, when the training wheels come off and Mr. Kulik stops like narrating the way through this, it gets, if you can't do it, if you can't understand now by yourself, it's going to be an unfair. And I don't want that to happen. So I'm just trying to like constantly check in and make sure everything is going okay. This will be where we're going to stop. This will be the last one we'll do today. This is one more layer of difficulty up now. So again, you've seen the difficulty switch. Start at relatively easy. We went up a notch for the previous problem. We're going to go up one more notch. And this is near maximum level difficulty here. So it says a water tank has the shape of an inverted circular cone with a base radius of 2 meters and a height of 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. Ay caramba, Mr. Kulik. This is kind of like, it seems like it has a lot going on. So we'll start with a picture. Does everybody understand what's going on, right? We have a tank, we're dumping water into it. We want to know what rate is the height of the water changing, which is going to be different at every height because the radius of the cone is changing at every height, right? Because the circle at the top of the water is getting bigger as the water rises, so it's going to be slowing down. The higher that water gets, the slower it's going to rise, because you need more water to fill to the next height. Everybody kind of see what I'm saying? Okay. So we'll start with a picture. So there's my cone. And inside my cone, I'm going to have a second cone of water. Everybody okay with that? And you're like, Mr. Kulik, why do you want a second cone of water? You'll see. And we have like, there's my water going in. Does everybody feel okay? All right. I'm gonna get rid of that. It was cute for a minute, but I don't really want it. So I'm going to have a radius for the cone. Actually, let's say, not for cone, we'll say T for tank. And a height for the tank. And then I'm going to need a radius for the water and a height for the water. Does everybody feel okay with what I've drawn and labeled so far? Why did I care about the radius and heights? How did I know those were going to be the quantities in question? Because a cone is, the dimensions of a cone are given as radiuses and heights, right? Remember from geometry? No? That's what you mean. So, which one of these are variables with respect to time and which ones are constants? Perfect, yes. So your water variables, or your water dimensions, are variables with respect to time. But your tank quantities, these are constants, right? The shape of the tank is never changing, right? The container holding the water, that doesn't get bigger or smaller with time, it stays the same. The shape of the cone of water inside that tank is going to be changing with time. Everybody feel good there? Now there's one other variable, I suppose, rattling around here. So since you're talking about filling the container, volume would be the other variable that's probably rattling around in the background here. So again, the volume of water will again be a variable. The volume of a tank, though, just a constant. So the volume of the water is just like the volume of the water. Everybody okay with the picture I've drawn and the labels I've given and how I've identified what's a variable and what's a constant? Okay. Next thing we need to do is go through and read the information and decide what these numbers, give names to these variables for the numbers, or give names to these quantities, I should say. So it says a water tank has the shape of an inverted circular cone with a base radius of 2 meters. What is that? The radius for the tank. And height 4 meters, so that'll be the height for the tank. Everybody okay here? Okay. If water is being pumped into the tank at a rate of 2 cubic meters per minute, what is that going to, what type of quantity is that? It's a rate, so what type of name is it going to give? It's going to get a derivative for a name. What should be the name of that derivative? dv, and I'm going to add a subscript w, just so we're clear that that's the volume of the water. It says find the rate at which the water level is rising when the water is 3 meters deep. What type of quantity is this? It's a rate, so it needs to be named as a derivative. dHW dt, yes. Anthony is on one today. And it's specifically asking when the water is 3 meters deep. everybody okay with how I've named everything here? So to relate volume, radius, and height in a cone, I'm going to use the volume of a cone formula. Everybody good with that plan? And we're going to just say that's the cone of water, because why would I differentiate the cone-shaped tank since it's all constants? It would just be 0 equals 0, and that doesn't really do much for me. The next step would be to differentiate both sides. Okay, the derivative of VW is dVW dt. Don't bother with writing the 1, even though we know it's there. The derivative of 1/3 R squared W HW. Not quite. Do you see that you have the product of two functions? Yeah, we need a product rule here. Oh no! That's going to be 1/3 times 2RW drW dt plus 1/3 RW squared. Oops. Sorry. Forgot. HW drW dt plus 1/3 HW. Nope. Yeah. Or sorry. R squared W DHW dt. Who sees a problem? Do we have that? Oh, I'm sorry. I circled the wrong thing. Yes, we're looking for that. But do we have this? We're not looking for that quantity, but we don't know it either. Guess what? We differentiated too soon. We have too many variables here. Because there we do not have dr dt. There's no way for us now to get dr dt. If I go and I plug things in, sure, I can solve for, I have a quantity for HW. I have a quantity, I'm looking for DHW dt. But I don't have RW. I don't have drW dt. There's no way for me to get those things from the information I'm provided. So this just won't work. Too soon. What I want to do is I want to rewrite this equation and get rid of this D or this RW in it. I need to look at my picture and look for a way to eliminate that variable, RW. And it looks like we're just about out of time, right? Yeah? Yes? Okay. Remind me where we left off. We'll pick up with how to do this when we get back next time. For you guys, just worry about working on the homework sets if you haven't finished them, and the multiple choice and free response for the test. Anything for 3-9 I want you to do, we'll do it together in class up until the test day. So you don't have to worry about taking that home and worrying about that at home. Worry about the test 3 stuff. Or current homeworks that you still have to catch up on. So don't worry about 3-9 stuff outside of class. We'll do all the 3-9 stuff I want you to do in class after test 3. Deal? Sound fair? I like that thing too. I was really excited though to talk about how we get rid of that RW. Does anybody see it? It's a geometric argument that you're going to have to make here. Anybody a geometry wizard? It's a similar triangles argument that's very good. 100% down. Way to go.